Now, once we have understood about the terminologies, now we can consider the common fluids available in the market, their composition, and when they are used. So, we discuss the fluids available for infusion. One of the commonest fluid, which is quite often referred to as balanced electrolyte solution. This term one quite often finds in the textbooks. Let's understand the meaning and the arduous labor involved by large number of research workers to develop this solution. The credit goes to Ringer, who experimented, and that was a classical experiment, when he found that when the frog's heart, a living frog, pithed frog's heart, its movements were chymographed. He found that given only sodium chloride isotonic solution, the heart kept on beating for a very little time. Then he added some potassium to it. Then it continued for a much longer time. This time heart stopped in a state of diastole, and he called it potassium inhibition. Then he added calcium in it. And then this time with this triple electrolyte, which are the major constituents, the heart kept on beating for a much longer time. Then he developed this concept of balanced electrolyte solution, and he made a triple chloride solution. The concentration was not good. It was up to Hartmann to modify this solution. So the present Ringer lactate solution is actually a Hartmann's solution. Now, so we discuss about the Hartmann's solution here. Most commonly, you will find that a balanced electrolyte solution is infused. If a balanced electrolyte solution is this Hartmann's solution, very commonly available in our wards. Why you call it a balanced electrolyte solution? Because it contains lactate, it contains sodium, it contains chloride, it contains sodium, potassium, and calcium, not only like saline solution where there is only sodium and chloride. So look at the composition. The composition of sodium, potassium, and calcium, and even lactate, is almost nearing the normal values of the plasma. And the most important thing is that the total anionic and cationic concentration is almost equal to or near to plasma, and the total osmotic pressure which it exerts is 274 milliequivalents, or it amounts to 274 milliosmol. So it is an isoosmotic solution. This is a solution most commonly used in our clinical practice because of its obvious advantages. Mind you, there is one flaw in it, that it contains lactate. It contains 28 lactates. So this solution is useful in most of the situation, but not in a case where there is alkalosis, like say in a case of pyloric stenosis where there is alkalosis. You can't infuse sodium lactate, which will in turn be converted into sodium bicarbonate, and finally you will aggravate the state of alkalosis. Therefore, we don't use it in alkalosis because it contains lactate. Otherwise, in shock and other conditions, when there is acidosis, this is a very good solution. Now let's come to potassium containing solutions. You have noticed that potassium is also present in the Ringer's lactate solution, but the amount is very low, and this potassium in most cases is not at all suitable for infusion. Now we consider the solution of sodium chloride most commonly used. Now the 0.9%, we must understand what we mean by percent. Actually, a percent, we commonly say that 0.9 gram of sodium chloride, mean the common salt, in 100 cc of water, though it should be 0.9 gram in 99.1 gram of water actually, but we roughly take 9.9 gram of sodium chloride in 100 cc of water. This makes 0.9% solution, and you must understand a 10% solution or a 20% solution is likewise interpreted. Now this is also called a normal solution, a normal saline, which is a misnomer. From chemistry point of view, this cannot be a normal saline, because a normal saline is actually 1 mole of a substance dissolved in a liter of water. But we commonly call it normal saline. But it is isoosmotic or isotonic saline. Why we call it isotonic saline? Look at its constitution. A 0.9% saline means it will have a sodium of 154 milliequivalents and 154 milliequivalents of chloride, making 308 milliequivalents of the total anion and cation. You know, it is well within the range of 310 milliosmoles of the normal osmotic pressure of the plasma. Therefore, it is an isotonic solution, or more clearly, it is an isoosmotic solution. Let's see how we have calculated that it contains 154 milliequivalents of sodium and 154 milliequivalents of chloride. It will require a bit of the knowledge of chemistry, especially the mole count. Let's try to, all books write that a normal saline or isotonic saline has got the strength of 154 milliequivalents of sodium and 154 milliequivalents of chloride. So you have got 154 milliequivalents of chloride and 154 milliequivalents of sodium. How did we calculate this? It is very simple to calculate, and there is not much mystery behind it. I will show you. Now, the 0.9%, if we talk in terms of liter, if it is 9 grams in 100 cc, then 0.9 grams in 100 cc, then it will be 9 grams in a liter. So 9 grams in a liter, you have to divide it by its gram molecular weight of sodium chloride. From the knowledge of chemistry, we know NaCl, the sodium has an atomic weight of 23, chloride has an atomic weight of 35.5. So together it comes to 9 by 58.5. Now, because this is the molar, so if milliequivalents, if we say, we have to multiply it by 1000. Now, if you calculate it, you get use your calculator and you will get 154. So we have arrived at the calculation that 0.9% sodium chloride solution will have 154 milliequivalents of sodium and 154 milliequivalents of chloride. Now, this solution is very commonly used, but one thing one must be clear about it, that if there is a huge sodium and chloride deficiency, probably this solution would appear to be very good. Unfortunately, if you notice at its chloride concentration, it is a bit higher than the plasma. If you remember, the plasma has got 103 milliequivalents per liter. You have got here 154 milliequivalents per liter. So it is actually a hyperchloremic solution. And if you infuse in large quantity, then there will be a state of hyperchloremia or increased chloride level. Now you know from the law of electroneutrality of the anions and cations that it will replace the bicarbonate ion. Kidney will have to expel bicarbonate ions to compensate the extra addition of chloride ions by your infusion. Now you have created a situation in which a state of acidosis has been created because you have given too much infusion of chloride ions. Therefore, everybody is warned that the sodium chloride solution given in small doses, a bottle or two, would not hamper. But resuscitating totally and entirely with sodium chloride, see in a case of shock or burns, there is always a danger of hyperchloremic acidosis. Now we have got another solution known as Halfcell, quite often used in pediatric practice. As the name suggests, it is very easy to calculate the Halfcell, because if 0.9% saline is the normal saline, Halfcell will be 4.5%, the milliequivalents will be equally halved. So you have got 77 milliequivalents of sodium in Halfcell, and in chloride you have got 77 milliequivalents. Why did we develop and why do we require this sort of solution? You try to understand that in pediatric practice, the pediatric kidney is not very efficient in handling sodium. It cannot excrete sodium. A large excess of sodium when delivered to the pediatric kidney, it cannot handle it. So we have to be cautious in infusing large quantity of sodium and chloride. So we have developed, and the pharmaceuticals have come with this new menu of Halfcell, 1/3 saline, 1/5 saline. Of course, they are supplemented by a non-electrolyte solution. Mind you, non-electrolyte means dextrose, which has no electrolytes in it. It is pure glucose. Such solutions are supplemented with dextrose with low sodium and are quite suitable for the infusion in pediatric practice. Now let's come and see that there is another saline which is hypertonic saline. If you remember the mean concentration, it is 142 milliequivalents. The range of sodium varies in plasma from 135 to 145 milliequivalents. So any fluid which delivers more milliequivalents than this is called a hypertonic saline. There are two types of such fluids available in the market. One is a 5% saline, another is 3% saline. as you have calculated, I have told you how to calculate the milliequivalents in a particular solution. It will be very easy for you if you want to calculate the sodium chloride 5% will have a sodium strength of 855 milliequivalents per liter, and out of which is of sodium, and the same the 855 milliequivalents of chloride. So total will be 1710 milliequivalents. Now you can grossly see that it is a very strong hypertonic solution or hyperosmotic solution. It will deliver a total osmotic pressure of 1710 instead of 310, which is the ultima thule or the maximum limit of the tonicity of the normal plasma. But we do need in certain situations, which I will tell you later. Another is 3% solution, and it is weaker, so it delivers, the 3% solution delivers about 513 milliequivalents of sodium and 513 milliequivalents of chloride ions. That is total of 1026 milliequivalents, or in other words, it will deliver an osmotic pressure of 1026 milliosmoles. Where do we need these hypertonic solutions? I have already told you about the normal. Let's come to the alkalinizing solutions available in the market. Now there have been recent change in the concept of the alkalinizing solutions, which were used very commonly. Now there are suggestions that their use should be restricted and are useful in only limited number of conditions. But let's see the fluid. We have sodium bicarbonate solution, and this sodium bicarbonate solution we have got. Then its sodium bicarbonate solution isotonic is 1.5%. It delivers 178 milliequivalents of sodium and 178 milliequivalents of carbonate. We have 75% sodium bicarb solution is a hypertonic solution, and it is usually not used, but an isotonic solution is more commonly used. One could use a sodium lactate, molar lactate, or 1/6 molar lactate. A molar lactate, when infused, is converted into sodium bicarbonate in the liver, and therefore produces counteracts acidosis. Now, far more important for us to see the clinical consideration, in what condition we would like to use this alkalinizing solution. Now, if the clinical conditions require water restriction, we use sodium bicarbonate solution, because sodium lactate solution 1/6 lactate, a large quantity of water has to be infused with it. The liver function must be adequate with lactates, otherwise you cannot guarantee that lactates will be converted into bicarbonates. Now, we do not use sodium lactate in cases of shock, because there is always a lactate excess in the blood in conditions of the shock. Now, what are the clinical considerations? We must ask a question: alkalinizing solution. The alkalinizing solutions alkalization solutions when and how much? Now we use these alkalization solution in a case of metabolic acidosis, but we should use this solution very cautiously. If the metabolic acidosis, we can treat the cause which initially produced metabolic acidosis, we should try to eliminate the cause. Say in example of diabetic ketoacidosis, it is the lack of insulin which has caused this metabolic acidosis. So the current teaching is that one should correct the metabolic acidosis in that case with administration of insulin, and there is hyponatremia, so sodium chloride solution, and other electrolytic deficiencies. In most of the cases, alkalizing solution is not needed. However, in certain cases, people have found that bicarbonate level is below 10 milliequivalent per liter. In that case, the tissues become irresponsive or unresponsive to drugs. Therefore, in that case, although the treatment of acidosis is to treat the cause or the metabolic disturbance which initially produced acidosis, but because of this low bicarbonate level, one has to infuse bicarbonate solution, and one should very cautiously use bicarbonate solution, and a full correction is never made. By full correction, I mean that the normal level of 23 milliequivalents per liter should never be achieved. One should try to have the level of bicarbonate after infusion up to 18 or 20 milliequivalents of bicarbonate after the correction. If we correct it to the level of 23 milliequivalents or 24 milliequivalents per liter, there is always a risk of metabolic alkalosis, because the respiratory compensation is going on, and the respiratory compensation continues in spite of the fact that the acidosis has been corrected. So there is always a risk of respiratory alkalosis. Therefore, we should not correct the acidosis up to the normal level of 23 milliequivalents of bicarbonate. Finally, we come to electrolyte free solutions. We come to electrolyte free solutions. Why do we need these electrolyte free solutions? The answer is very simple. You might have a compromised renal function. In that case, one has to administer the electrolytes, considering the capacity of the kidney to excrete these electrolytes. Moreover, the fluid is also required along with electrolytes. So if we have been able to fulfill the requirement of the body with electrolytes, it is always nice to infuse the electrolyte free solution with water. But one thing must be considered, that these solutions have to be isotonic. So what are those solutions? It is glucose or dextrose solutions are best substitute as electrolyte-free solutions. Let's see what are the choices available in the market. It is, let us say, it is 5% dextrose. And again, we must be able to see what is its osmolarity. A 5% dextrose means 5 gram in 100 cc, so it is 50 grams in a liter, and the glucose has a gram molecular weight of C6H12O6. So we have a gram molecular weight of 180, and we multiply it by 1000 to have in milliequivalents. Then it will come that the 5% dextrose exerts a total osmotic pressure of 278 milliosmoles. So 5% dextrose is a isoosmotic solution. The 10% dextrose, 20% dextrose can be used, but they are all hypertonic solutions. What is the advantage of using dextrose? It is electrolyte free, so you can administer water through it. And secondly, dextrose provides energy for the body. 1 gram of glucose provides 4 kilocalories of energy. So therefore 5% dextrose in 500 cc will be 25 grams. So one bottle will yield 100 kilocalories of energy. So it also provides energy. Another thing in transfusion is fructose 10%. This was very commonly used only 10-20 years back because it was this idea was given credence that theoretically fructose can be metabolized in absence of insulin. So it was helpful in ketoacidosis and liver disease. We quickly understood that this fructose has no advantage, and many times in many YouTube videos you will find that they say any amount of fruit you take, diabetics will have no problem. This is a very wrong and actually theoretically incorrect proposition. Now fructose, what is its advantage? Its advantage is that it makes entry into the cell, and possibly the glucose 6-phosphate which is formed is short-circuited by this fructose, and directly you get fructose 1,6-phosphate 2 steps ahead in the glucose metabolism. But what disadvantage it has? From glucose to glucose 1,6-phosphate, which is insulin dependent reaction, this reaction is very important in the body because it is a sort of not only committed reaction but rate limiting reaction. Only that much amount of glucose will be phosphorylated, which when the glucose 6-phosphate is consumed, then only glucose will be phosphorylated. This rate limiting reaction is surpassed by fructose, so large quantity of fructose is metabolized, causing excess consumption of ATP, hypophosphatemia, and this is not a myth. In pediatric practice, people have noticed this syndrome of hypophosphatemia because of fructose. And see, ultimately, the lack of insulin will prevent and bottleneck the metabolism of fructose at the level of pyruvic acid. So there is no, fructose offers very little advantage in absence of insulin. Now this dextrose, you can infuse 5%, 10%, 2.5% or 20%. बंद कर दो, नहीं इसको हम कहते हैं. What should be the rate of infusion of dextrose? What should be the rate of infusion of dextrose? Infusion of dextrose. The rate of infusion of dextrose should be maximum 5 milligram per kg per minute. If you infuse faster, infusion rates and greater concentration of glucose, there is always a chance of having glycosuria. So therefore, one should be careful that the rate of infusion of glucose should be within the prescribed limits. Thank you. These solutions containing potassium. Potassium containing solutions. You have seen that the ringer lactate contains a small quantity of potassium. It is all right, good for maintenance, but when there is a severe potassium deficiency, then you have to supplement, and we have to supplement potassium. The common potassium supplement is potassium chloride. It comes in ampules having 1.5 gram ampules. 1.5 gram ampules. Let us see how much milliequivalent it contains. You see, 1 gram or 1.5 gram of potassium will have a 1 gram, let us see, 1 gram of potassium in the form of KCl is 1000 milligram, and divide it by the atomic weight of potassium, that is 39, and plus chloride is 35.5. Now it comes to 13. So 1 gram of KCl will have 13 milliequivalents of potassium and 13 milliequivalents of chloride. In total, 1.5 gram of potassium which you are infusing, you will be infusing 20 milliequivalents of potassium. Now, potassium has certain rules for infusion. The patient must not be anuric or oliguric. Patient must be fully hydrated. Hydrate the patient and then only give potassium. The only way to know the hydration is that the patient will have good urinary output or normal urinary output. You don't start potassium infusion in anuric or oliguric patients. Then the second thing is, potassium is never given in bolus injection. It is always diluted in a bottle of saline or possibly dextrose. Then the rule is that not more than, usually we see not more than 120 milliequivalents. What are the rules of potassium infusion? Never in oliguric patients. Patients must be hydrated. Must be hydrated with normal urinary output. No infusion should be given in bolus. The ampoule should be diluted or pushed in the bottle of saline. And lastly, it should not be more than 120 milliequivalents in 24 hours, and the concentration of the solution, concentration of the potassium solution should never be not more than 80 milliequivalents per liter.